Okay, I know I saw you guys yesterday. This is one of the people circles that in Radians, and today we start rotational motion, which unfortunately is probably one of the hardest topics for this semester. So follow along. Okay, before we really get to rotation, let's talk about what we actually covered. Right? We discussed kinematics. That was the start of the semester. It was displacement, velocity, acceleration. The idea is to describe it. Right? So kinematics is literally just a study of describing. We're not talking about in the kinematic form as to how we're doing the set, what order of acceleration and all that stuff came in as a whole. Right? So similarly with rotation, we're going to start with kinematics, which means how do we describe rotation? And then we move on to dynamics of rotation, which is what causes to start to rotate. Rotational kinetic energy, since something that's rotating is moving, it has rotational kinetic energy. And of course, angular momentum, because just like linear momentum, which can be conserved in the absence of an external force, angular momentum is another conserved quantity, and we should hopefully end with that. Don't worry, we're not going to do all of that today. It's 3 lectures. And today, all we're really going to do is focus on units and kinematics. Okay, the idea of rotation is we're going to start with using slightly different units as we're using so far. So take a little time today to get comfortable with it. And next week, be super comfortable with it because we're going to have to move pretty fast. Having said that, I do know that the Tuesday, Thursday sections this week have only one recitation. The homework, which was due Monday, the online homework, has now been extended to Wednesday so that you have time to ask your instructor. The written homework, which will become available today, is due as scheduled next week. And of course, there's a pre-lecture on this due for Monday. Okay, so now let's extend what we've covered so far to rotational motion. And the first thing, of course, is discussing what is rotation. So rotation is that, right? It is an object moving about some axis in the object. It's not the same thing as moving in a circle, right? We've already covered an object moving in a circle. Okay, rotation, the moving in a circle part is that right? An object revolves around something, that object is moving in a circle. A rotating object is something that varies. Right? It's a rigid point objects, right? What we've studied so far cannot rotate. Right? If I just have a single point, which is like infinite as being small, there's no sense in that rotating. It can move in a circle, it's not rotating. But once we get to a rigid point, right? A rigid object which has some spatial dimension, right? It is allowed to move. Everyone will be so far. Okay. Consider the snail in this picture. It does 2 things, right? It's trying to get away from a predator, I believe, so it's moving away. And it chooses to move away by rolling away as opposed to slowly going away. Because the speed with which it's capable of rolling away is much faster than the speed with which it's capable of walking. This making sense? Now, when it rolls, it's undergoing 2 kinds of motion. Translational motion, right? It's moving along a straight line, right? And we describe that kind of motion using the kinematics we've already studied. Right? But apart from that, it is also rotating. Does everyone see that? Right? So now we have to separate that rotation from that translation. Right? In general, a lot of objects, like the dancer from the end of the slide yesterday, right, was undergoing parabolic motion in their center of mass. Right? But they're allowed to rotate about their center of mass while they're in it. This making sense? The Earth is another example. Right? The Earth as an object, that is treated as a point object, is moving in a circle around the sun. Right? It is describing a circle, and that circle we can describe using centrifugal forces and centrifugal acceleration. Right? But while it's doing that, it's also rotating about its own axis. Right? So now we're going to focus on the rotation part. Right? The translation stuff is already done. What you cover in Newton's laws and So, the idea is to think of a translational quantity and think of its rotational angle. So for the next week and a half, every time we come up with a rotational quantity, to really understand how it relates to other quantities, right? Think about the translational quantity, right? And how that relates to us. Because you know how displacement relates to velocity. You know how velocity relates to acceleration, right? The idea now is to build rotational counterparts to those quantities, right? So, in translational motion, we measure position or displacement as x, and our unit is typically, what's the SI unit of displacement? Meters, right? When something is moving in, like, rotating, we discuss change in angular position as opposed to change in just position, right? So we're measuring changes in angle. Everyone with me so far? Right? When an object rotates, the difference between an object rotating this much and that much is just the angle it's rotated through. Right? So that is similar to how far an object has moved translationally. Okay? The next topic was velocity, which was the rate of change of displacement. Right? So similarly, we describe a quantity called angular velocity. Right? The symbol for which is omega. That W is actually a negative rate. And omega describes how fast an object is moving. Right? So just like V describes how fast an object is moving, right? How fast its displacement is changing. Omega describes how fast an object is rotating, or how fast its angular displacement is changing. Right? Like how much angle is it covering per unit? The faster something rotates, the more angle it covers per unit. Right? And finally, we ended kinematics with acceleration. And acceleration in kinematics was defined as the rate of change in velocity. And similarly, for rotation, we describe something called angular acceleration as the rate of change of angular velocity. Right? So think of stuff spinning up to speed and spinning down to speed. I'm pretty sure none of you are old enough to remember ceiling fans, but you must have seen them move. Right? They used to hang on ceilings. I don't know if they have them here, but and then they spin. Everyone knows what a ceiling fan is, right? Okay, you turn it on, and it spins up to speed. Correct? Right. So it's undergoing angular acceleration because during that time period, its angular velocity, how fast it's spinning, is changing. Does that make sense? Right? Just like linear acceleration was how fast was the rate of change of velocity. Right? The angular acceleration is the rate of change of angular velocity. Everyone with me so far? Okay. So these are quantities, and now we have to try and figure out how they relate to each other. Right? So these are your translational analogs of rotational quantities. Right? We know how those guys relate to each other. Right? Now we're going to try and figure out how these guys relate to each other. Okay? So, your translational thing was V is delta x over delta t. So now we have rotation is delta theta over delta t. And acceleration was delta v over delta t. And now we have alpha, which is delta omega over delta t. Okay, now the math. Typically, we measure angles in degrees. We typically actually measure angles in degrees, right? The SI unit for angle is degrees, which is not the same thing as degrees. Does anyone know the actual conversion between radians and degrees? Think about how many degrees are there in one full circle. 360 degrees in one full circle. How many radians are there in one full circle? Close. 2 pi. Right? It's 2 pi radians in one circle. Okay, which gives you your conversion factor. So the conversion factor is 2 pi radians is 360 degrees. This is one revolution. Everyone agree? One full circle, right? The change in angle is 360 degrees or 2 pi radians. Okay? Your calculators can be in degrees or radians, and it's up to you to know which. Right? The SI unit for angle is radians. So from now onwards, when we're dealing with angular quantities, we're going to be working in radians. Okay? So remember to convert. So, we can do an example conversion. So if I want to know 30 degrees in radians, right, I need to multiply it by 1 such that the degrees divides out. So that's 30 times 2 pi radians divided by 360 degrees. Right? So the degrees goes away, it's 60 pi radians divided by 360. Everyone with me? Right? It's a straightforward unit conversion to get from degrees to radians. The more important one that you'll use a lot more is that 2 pi radians is one full revolution. Okay? Right. Now, the reason we use radians, right, as opposed to degrees, is geometry. Right? If I have a circle of radius r, right, like shown in the figure, if I travel the distance delta k, if I rotate the distance delta k, that's an angular distance. Correct? Then I move some length of arc. Everyone follow? So, if I draw it, and don't laugh at my circles, so that's a circle, right, of some radius r. Right? Let's say I'm talking about moving from here to here, right? That's rotating. Correct? Then the length of this arc, let's call that S. The radius of this circle is R. And let's say delta theta is that change in angle. It's the measure of that angle. Does everyone follow the geometry right now? Okay. So as delta theta gets larger, the arc length gets larger. Right? And as R gets larger, the arc length gets larger for the same delta theta. Everyone with me? Okay. The fun part about using radians, and I use the word fun lightly, is that the angular displacement, right, that delta theta, if you measure it in radians, it is the ratio of that arc length to that radius. Is everyone following? If I measure that angular value, right, if I measure this angular value, right, in degrees, okay, then there is no set relation between S and R. Okay, but if I measure this angular value, let's say it's 30 degrees, right, and I converted that 30 degrees to radians, right there, correct? Right. Then that value is also equal to the length of this arc divided by the radius. Everyone with me? Right? This is the reason we use radians. Right? So it's the angle subtended by an arc of length S in a circle of radius R. Does that make sense? So the angle subtended by a full circle is 2 pi. Everyone with it? Right? And that's related to why the circle is 2 pi. Okay. So, remember, use radians for angular displacement. Okay? And when you use radians for angular displacement, the length of arc travel, right, the actual physical distance moved, can be related to the angle change. Right? It's a simple ratio. S over R is equal to K. Everyone with it? Okay. Right. So, let's consider a rigid body. These are wind turbines. Right? So, these are rotating wind turbines. This every point someone rotating something on a straight line. Correct? You don't want to get hurt. You stop them closer to where they're rotating from. Right? As opposed to towards the end. Right? And this picture actually shows that. If you notice, wind turbines are blurred towards the edges. Right? Indicating they're moving faster at the edge. Does that make sense? If their actual speed is higher at the edges. Everyone with me? Okay. But what about their angular speed? So we agree that different parts of the turbine, right? And you can think of this as sitting on a merry-go-round. Everyone knows what merry-go-round is, right? Okay. So think of it as sitting on a merry-go-round. And you're faster towards the edge. If you want to have fun on a merry-go-round, you will sit towards the edge. Everyone with me? Okay. So we agree that the actual speed changes depending on how far you are from the axis of rotation. But what about the angular speed? Does that change? The angular speed is the rate at which the angle changes, right? Correct? So if I describe this, like this turbine, using that, it looks something like this. Right? Like a freeze frame of it will look something like that. Correct? So every single point along that plank, right? Every single point along that turbine, as it moved, covered the same amount of angle. Correct? Right? So if you think of this pen as the plank, as it rotates, right? This point has moved a greater distance than this point. Right? Which is why we're saying that this point is moving faster than this point. But in terms of the angle rotated through, every single point on this line has rotated through exactly the same angle. Does that make sense? Right? In order for different parts of this line, like this pen, to have moved different angles, this pen would have to break. Does that make sense? Right? So what we're saying is when we do this, every single part of this object undergoes the same angular displacement in the same amount of time. Right? Which means that every single part of that object has the same angular velocity. Everyone with me? Okay. So now, we know that the length of the arc, right, is r times del theta, right? That's the reason we picked radians to begin with. If I'm working with angles in radians, I can say that the length of arc traveled, right, the actual distance moved at this point as this underwent rotation, right, is r, which is the radius, times delta theta, which is the change in angle measured in radians. Everyone with me? Okay, so if that's the change in position, the speed is the rate of change in position. Right? So it's r delta theta over delta t. Everyone with me so far? Right? So what we're saying is the displacement, right, this guy, S, is r times delta theta. Right? So the rate of change of displacement, delta S over delta T, which I call V, right, the speed, is the rate of change of r delta theta. And this quantity is omega. Right? So I can write V equals r omega. And if you forget everything else from lecture today, right, this and radians are the two things I want to do. You can relate the translational speed of any object that is rotating, right? But this is far away from the axis of rotation to its angular speed. This makes sense? Right? It doesn't give it time to think about it. This is not that straightforward. Okay? But that relation tells you that, I mean, it explains your merry-go-round, right? As r, which is the distance from the axis of rotation, increases, the speed increases. so remember V equals R omega relates your translational speed V to the angular speed omega. Everyone with me so far? Okay. So, we can relate displacement, which is S or X in this slide, with R theta, as long as theta is in radians. We can relate V as R omega, as long as omega is in what unit? What must be the units of omega? V equal to R omega. Omega is delta theta over delta T. Right? Delta T I enter in seconds. I measure delta theta in what unit? Radians. Right? So this expression works when you work with omega in radians per second. Everyone with me so far? Right? So your first step before using any method in rotation is to make sure you're in the right units. Right? Just like we had to do with translation, right? To make sure you're in the x-axis, to use the rotational quantities, make sure you're in the x-axis, which is radians. Everyone with me? Okay. Angular acceleration is speeding up or slowing down in a circle. There is a different kind of acceleration which you are familiar with, which we'll come to after I see if you're awake. That is a bicycle. Well, it's more like a radar, but still it is. I really should stop checking. But yes, every single point can be described by the same angular velocity. Right? It's different points on the rigid object for describing different angles in the same amount of time. Right? That means different parts are moving with different angular speed. That's not possible with the object is rigid. Correct? So, yes, we describe all parts of the rotation of that object with the same angular speed. Okay, so I'm going to close this. Right, I think this is some version of Bonnie and Clyde, which, as far as I know, wasn't a very good story. But okay. You have two bunnies sitting on a merry-go-round. And for some reason, they call it Bonnie and Clyde. And I'm asking you about their angular velocity. Right, so if I'm asking about angular velocity, right, the quantity I'm talking about is omega. Right? So do they have the same omega or different omegas? I'm going to wait a bit before I check and see where you are. Right, let's see where you guys are at. Okay, can we fix this? We're looking for angular velocity on a rigid object. Right? Every single point on that rigid object must rotate with the same angular velocity. Right? As it moves, every point on that line covers the same change in angle. Right? So angular velocity is measured from past angle changes. Every single point on that merry-go-round is undergoing the same change in angle per change in time. Everyone understands? Right? So I can't actually see the options anymore, but I think they're back there somewhere. Yes, the same as Bonnie's, right? They have the same angular velocity. Okay, I'm going to close this and we're going to try another one. body of iron. Okay, let's take a look. Very good. Right, so we all understand that the one further away from the axis of rotation is physically moving faster, right? With the same angular velocity as any other part of that system. Okay. Close this. And now, let's do a little bit of math. So, this is talking about a turbine blade that is rotating at 25 revolutions per minute. Now, the reason for this question is literally that, okay, that unit, revolutions per minute, comes up in the top. Right? It is not the SI unit. Right? First off, identify what is a unit of. What physical quantity should I describe in revolutions per minute? Is revolutions per minute linear? No, right? It's a measure of how fast something is rotating. Right? So revolutions per minute is a unit of omega. It is not the SI unit of omega. Right? It is a unit of omega, which we will need to convert to the SI unit. This making sense to it? Right? Number of revolutions per minute is basically describing how fast something is rotating. Right? The SI unit for how fast something is rotating is radians per second. Right? So my first step in this question has to be to convert that given omega, right, to radians per second. And then I can find the translations of different objects on that unit. Right? We know that V1 must be less than V2. V1 is closer to the axis of rotation. So that part of the blade is not moving as fast as the other part of the blade. Correct? Okay, so let's do that conversion. So I'm given omega as 25 revolutions per minute. SI unit is radians per second, right? So the conversion factors I want to use are 1 revolution is 2 pi radians, and 1 minute is 60 seconds. Everyone good so far? Right. Remember, I want to divide the minutes out, so let's get the 1 minute up top and the 60 seconds down here. I want to divide the revs out, so the radians go up top and the revs go in the bottom, so that, and that. And I'm left with 25 times 2 pi divided by 60. Pi is 3.14. Can someone actually do the math and tell me the number? Who has a calculator? 2.61. So it's 2.61 radians per second, right? That is the SI unit. Now when I want to know how fast an object, or how fast the part of the blade that is R1 away is rotating, right? So V1 is equal to R1 times omega, right? So I know that R1 is given in my question to be 0.5 meters. This multiplied by 2.61 radians per second, right, gives me like 1.3 meters per second. Radians has no dimension. It's a ratio. Right? It's the ratio of the length divided by length, right? The arc length over the radius. Right? So radians as such has no dimensions. That makes sense? So when I multiply radians per second with meters, I get an answer in meters per second. Everyone must be so far. Right? Radians are a dimensionless units. Okay? Okay, so and when I want to find out how fast V2 is moving, V2 is just R2 times omega, which in this case R2 is 1 meter times 2.61 rads per second gives me 2.61 meters per second, right? What we've used here, of course, is that omega is the same at both these positions, R1 and R2. Everyone with me? Right? So remember, convert revolutions per minute to radians per second. Okay? You can work in radians per second. Revolutions per minute is a common unit. Right? Not the unit you ever want to plug into it. Okay? Right. Now let's get to acceleration. We describe acceleration when we were doing translation motion as delta V over delta t. And it's attempting to do delta omega over delta t as angular acceleration, and that is normal. Right? Alpha, what we call angular acceleration, is delta omega over delta t. So alpha only exists when something is speeding up its spin rate or slowing down its spin rate. Correct? It's delta omega over delta t. So delta omega should not be 0. For alpha to not be 0. Everyone with me? Right? That's just like the linear algebra, right? Where you describe A as delta V over delta t. So speed doesn't change. A is 0. Right? That kind of speed. But we covered another kind of acceleration in moving in circular. Correct? And we call that centripetal acceleration. That is required to move in a circle. Everyone with me? Okay. So what we're saying now is think of that ceiling fan again. Right? As that ceiling fan is spinning up to speed, right? You turn it on, it spins up to speed. There is some alpha. Omega is changing. Correct? Then it spins at a constant omega for a while. And then you turn it off and it spins down. During the spin down process, there is alpha as well. Right? Again, angular velocity is changing. Correct? Okay. But what about the part where it's just spinning at a constant rate? Omega is not changing. Right? During that portion, alpha is 0. Right? If omega is not changing, delta omega over delta t is 0. Everyone with me so far? But because every single part of this is moving in a circle, it must have centripetal acceleration. It must have an acceleration pointing towards the center of that circle. Right? Even when it's spinning in a circle with constant speed. Does that make sense? Right? We covered that kind of acceleration before, and it was v squared over r. Right? In order for an object to move in a circle with a speed v, right, in a circle radius r, you need an acceleration of v squared over r. Everyone remember that? That's it too. Right? So everything moving in a circle, like every single part of this rigid object that is rotating, right, must be undergoing centripetal acceleration. Everyone follow me so far? Right? And we said centripetal acceleration is v squared over r. And now we know that v is related to omega. Right? We can relate v, the speed with which it's moving in that circle, to the angular velocity with which it's moving in that circle. Right? And if we substitute v is equal to r omega in the expression for centripetal acceleration, we get another expression for centripetal acceleration, which is omega squared r. Right? So, centripetal acceleration is r omega squared. It exists anytime something is moving in a circle with an angular speed omega. Everyone with me? Right? There is no requirement for omega to be changing. Right? Alpha, on the other hand, right, can be related to the tangential acceleration. Alpha only exists when omega is changing. Right? So when this object is increasing its spin speed or decreasing its spin speed. Right? But regardless, it will always have centripetal acceleration, which is omega squared r. Everyone with me so far? Okay. So we can relate the tangential acceleration to alpha as r alpha, right? This will only happen when something is slowing down or speeding up in terms of its angular speed. Okay. By a show of hands, how many people in this class have actually used a centrifuge? I figured more than me. But we all know what a centrifuge is, right? What's it supposed to do? Separate blood components based on weight, right? And the idea of separating, right, is you're looking for a force, right, that separates based on weight. Right? Typically, we do have such a force, and it's called gravity. Right? Heavier stuff will displace lighter stuff. Right? Heavier stuff needs more force. Right? Due to gravity. However, sometimes those weight differentials aren't quite that much. Right? So we want some way of creating a force that does separate based on weight. Right? So it has to be based on m. Everyone with me so far? So when we put stuff in a centrifuge and it spins, right? So if you turn it on, it's spinning at some constant rate. Right? That's where the separation is happening. Correct? Okay. So it's spinning at some constant rate. Are those particles undergoing acceleration? Yes, right? They're spinning. Very good. Right? What kind of acceleration? Centripetal acceleration. Right? So every single particle in that centrifuge is going to experience centripetal acceleration, and centripetal acceleration, as we just saw, is r omega squared. Correct? Okay. Centripetal force would be m times the centripetal acceleration. Does everyone follow that? The centripetal force should be mass times acceleration. Right? So the force required to get this object to move in a circle of radius r with an angular speed omega is m r omega squared. Right? So what we see here is a force that depends on m. Correct? Okay. And on r. Right? So the particles further away from the axis of rotation are experiencing greater centripetal acceleration, greater centripetal force. Does that make sense? Right? As r increases, the value of that number increases. Right? And r is the distance from the axis of rotation. Right? Now, let's say I have two objects of different length. Which one requires more force? The large end or the small end to rotate in a circle? The large end, right? Correct? They're all rotating in that circle with the same omega. Everyone with me? Every single part of those black constituents is rotating with the same omega, right? But the heavier stuff needs more force to rotate, right? So it moves to a larger r, it goes further up. In doing so, it pushes the lighter stuff out of its way. Does that make sense? Right? So since you need more centripetal force to rotate something in a circle of larger mass, right, the heavier mass goes towards the end of the rotation. Right? Thereby displacing the lighter. Right? Creating like a pseudo gravity. Does that make sense? It's separating based on density. Right? Because as r increases, fc will increase. Omega is the same energy. Right? So masses closer to the axis of rotation of the centrifuge experience less centripetal force than masses further away from the axis. Right? So the greater mass should move further away. They need more force. Okay. Right, let's do a quick question on centrifuges. Okay, this is a bit of math. You're not going to do this in your head. I should see pens and pencils. Or pens and paper. What is my first step? Convert that 15,000 RPM stands for revolutions per minute, right? So convert that 15,000 RPM to radians per second. Once I have that, my next step is to find the centripetal acceleration, which is r omega squared. I know r, and once I convert the 15,000 RPM to radians per second, I know omega. Right? That will give me the centripetal acceleration in units of meters per second squared. Right? And I'm asking you to express your answer in terms of G. So what that means, of course, is 1 G is 9.8 meters per second squared. Whatever you get for your A value, divide by 9.8, and that's the number of G. I do want to look and see where you guys are, but early morning math is generally so much fun. Right, let's take a look. Nope. Okay, if you guys are doing this correctly, some of you are. Centrifuges provide a heck of a lot of energy acceleration. Should be significantly more than G, otherwise there is a condition to us. Yes, right. Click something. If you didn't get that answer, practice the algebra. It's fairly straightforward. It's that unit conversion that's the most important step. Okay? Right. Okay, so we have our analogs to kinematics. So we had kinematic equations, right, describing how the kinematic properties, displacement, velocity, and acceleration relate to each other. So just like that, we have rotational analog for kinematics, right? This is now talking about an object that is undergoing uniform angular acceleration, right? So it's a ceiling fan spinning up the speed or spinning down the speed, right? Delta theta replaces x, right? Just like x was the change in linear position, right? We replace x with delta theta because delta theta is the change in angular position measured in radians, right? We replace v with omega, right? Since this implies an angular acceleration alpha, we'll have an initial omega and a final omega, right? So when a ceiling fan spins up the speed that happens. And all your kinematic equations translate that way, right? You can literally take the linear translation of kinematic equation, substitute the angular quantity in place of the linear quantity, and use the same equations to describe rotational motion as opposed to linear motion. Okay? I'm not going to torture you guys too much with questions on this. You've seen enough kinematics. This is just more kinematics. It's kinematics in a circle. The dynamics is a lot more interesting. Okay, before I let you go, so a speedometer is supposed to measure its speed. I would like my speedometer to be measuring my speed. Let's say that it's actually measuring omega, which is the angular velocity, and it computes the translational velocity from its measurement of omega. Right? And the relationship between v, the translational velocity, and omega is what? V equals r omega, right? Correct? Remember that, v equals r omega. Okay, so what this problem is actually doing is it's measuring omega. It knows the size is higher, so it's multiplying that radius with the omega and giving you your speed. Right? Let's say you're using the tire of the wrong radius. So it will obviously be the wrong speed. Correct? Because it's multiplying by the wrong r. Right? It's measuring omega and multiplying by r to get you a speed. Right? You're using a tire of different r than what it thinks you're using. So is the speed it's reading going to be more or less than your actual speed? So you're using larger diameter tires, right? Correct? Right? So your actual V's are larger than the omega. What the system is measuring is r smaller than the omega. So is it going to be reading less than your actual speed or more than your actual speed? It thinks you're using a smaller tire, right? Correct? Right. If it thinks you're using a smaller tire, it's multiplying the omega against a smaller number than what it should be multiplied. So it will be less than how fast you're actually. Right? Okay, I will see you guys bright and early on Monday. Remember, do all your homework, pre-lectures. Have fun with rotation.
You told us to find the force of the curator.
Yeah?
Yeah, and I couldn't figure it out. I have all my units and everything, but to find the force of the curator.
I'm not seeing enough forces. There's friction in this question, right?
Yeah. Are you found